So we are here again in our seventh webinar meeting of our colloquia on portable X-ray fluorescence, which is organized by the European Academy of Science and Arts, the STEMAC Expert Group Project, and the Global pXRF Network. For our academy, this is a follow-up on a specialized section of the successful colloquia Arts Meets Science and a further activity of STEM in Arts and Culture Expert Group. Myself and Michaela wish to express our gratitude once more to Kelly Ricks, who could not be here for personal reasons, and Doris Klida from the Academy for their immense technical help in organizing this colloquia. Today we have two speakers, Dr. Mai Abdelgawad, Centre d'études Alexandrines and Université Bordeaux, Montaigne, France, and Dr. Camille Frugier, Centre d'études Alexandrines and Université Poitiers. I would pass now on the online podium to Michaela to introduce the first speaker and start with the first presentation.
Thank you very much. I have the great pleasure of introducing Mai Abdelgawad. She holds a diploma in archaeology and has a master in chemistry from the University of Alexandria. Since 2013, she's a chemical engineer at the Centre d'études Alexandrines. I'm so sorry for my French pronunciation, so please, if you're a French speaker, just hold your ears. She's working there on material characterization and specialized in ceramics, but also works on the development of using pXRF in archaeometric settings. She's a third-year PhD student in archaeological sciences at the Université Bordeaux, Montaigne, and she's also one of the main forces behind the success of the portable X-ray fluorescence ceramic user network that was financed by the Cnrs and included a couple of different laboratories around the Mediterranean, but later also as far as Köln. And it was hosted from 2021 to 2022 to 2025 by CLX and had a great closing session in Alexandria this year. The whole network focused on creating a standard set for ceramic analysis and inter-device comparisons, and Mai was one of the main givers of ideas and leaders there. She's also part of the core team of the Go pXRF network, which we are very, very proud to have her. And with that, I would like to hand on to Mai.
Thank you so much, Michaela, for this quite amazing introduction. I would have never used these words to introduce myself, so thank you very much. And thank you, Ioannis, and I would have thanked Kelly for all the work that she has done to prepare this session. So today I'm going to share my experience of more than 10 years of using portable X-ray fluorescence, particularly within my framework, the Centre d'études Alexandrines in Egypt, and how the results have been monitored and the protocol of measurement improved. The development of portable X-ray fluorescence had made it possible to collect larger. Can you hear me well?
Yes.
Has made it possible to collect larger quantities of data on ceramic analysis, despite the lower sensitivity compared to traditional analytical techniques, such as the WD X-ray fluorescence and the ICP-MS. Since the establishment of the Materials Characterization Laboratory of the Centre d'études Alexandrines, practical challenges such as time, space, and archaeological samples export and import have been addressed by acquiring portable and semi-portable instruments. Therefore, the laboratory now, we have 3 portable analyzers, a Eton that we have acquired in 2013, which I have been using since then, a second Eton which we purchased in 2016, and recently we have purchased an Olympus Vanta. These devices allow us also to support visiting teams working in Egypt and to conduct on-site analysis and data collection across different locations. The results here are based on the data obtained by only one Eton, which is the oldest one acquired in 2013, where I will present to you the protocol of measurement, the different modes used for the analysis of the clay-based materials, and the impact of the protocol and this portable equipment on the precision and accuracy of the acquired data. Before starting the measurements, the Eton is warmed up for 1 hour and a system check is performed to verify the proper functioning of the device. A reference check sample is then measured twice each day, once before and once after after the measurements. And this is done to verify the stability of the calibration of the device. The temperature and relative humidity are also measured at the same time with the measurement of the reference sample to ensure the stability of the working environment. For the ceramic samples, fresh breaks are prepared to provide the best results. These breaks must be at least 3 centimeters long and 1 centimeter wide to cover the 8 millimeter length of the equipment and to minimize the X-ray scattering. 3 measurements are performed on 3 different points on the fresh break due to the heterogeneity of the clay matrix of the ceramic material. The equipment is automatically then set to calculate the average of the 3 measurements for each sample, and these averages are used to perform the multivariate statistical analysis. At the beginning, both mining and test all-GU modes were used for the analysis. And then finally, I chose to only choose the mining mode for my analysis because it provides a more stable and consistent results, where mining mode applies a single well-defined calibration that is optimized for geological materials with higher elemental concentrations. On the other hand, test all-GU mode, while useful for unknown and mixed material, automatically switches between soil and mining calibrations, which can introduce a variability in the data and make long-term comparisons more difficult. So relying on the mining mode was to ensure that all the measurements were based on the same calibration model. Each measurement takes 360 seconds, which allows optimum time for each filter, calculated at 90 seconds for the main filter, 90 seconds for the low, 60 seconds for the high, and 120 seconds for the light elements. The duration for each filter has been tested against the errors, where for the first filter at 90 seconds, we can see that most elements can be measured with almost the same error at 60 seconds. These elements remain, however, with a lower error value at 90 seconds. Similarly, for the second filter, for the low elements, shows results with acceptable error value. For the measured elements for this filter, such as the chromium, vanadium, titanium, calcium, and potassium, which were measured at 90 seconds. The third filter showed an error for barium at acceptable rate at 60 seconds with respect to the error value noted at 90 seconds. For the fourth filter for the light elements, we can see a decrease of almost 100 ppm specifically for the silica and magnesium at 120 seconds. To summarize, we noted that for the first filter, we have a decrease of error of 1% for most elements except manganese, which decreases by 2% from 60 to 90 seconds. For the second, a decrease of almost 3% in error occurs when changing time from 60 to 90 seconds. For the third filter, almost no change, or that of around 0.5% occurs with the third filter from when changing the analysis duration from 60 to 90 seconds, while the fourth filter gives an error decrease of around 2 to 3% at 120 seconds. The next step here was the follow-up of the reference sample used to check the stability of the calibration, accuracy, and precision of the device. At first, in 2013 and early 2014, a non-reference ceramic sample was used to verify the stability of the device. And later in 2014, when we acquired a certified reference kit, we began systematically using 2 standard NIST samples, one of an agricultural soil sample and another of a waste sample from a mine site. This second sample has been analyzed during the early years in mining and test all-GU modes. In this part, I will also show the effect of regular factory calibration and the influence of the collimator setting on the results. First, while no certified sample was available at the beginning of 2013, some systematic errors have been noticed in the measurements, especially for the light elements. And so a first factory calibration has been applied in 2014. And since then, precision tests were regularly performed, at least twice per year, to verify the precision of the results, and systematic factor calibration was applied to the device to verify the stability of the acquired measurement, at least in the precision of the data acquisition. In 2019, for this equipment, the X-ray tube has been changed due to its failure, and from 2019 till 2024, no factor calibration has been applied, and the last factor calibration applied was in mid-2024. To be able to present for you the results, I have given each calibration period a number from 1 to 7, and here only the results from 2 to 7 will be presented by calibration period and year, showing the results of only the certified samples. For the results of the reference of the certified reference checked samples, we noted the good precision of the equipment, but a shift in accuracy, mostly related to equipment bias, has been noticed. For the major elements, we observe a systematic bias in the equipment results, where silicon and aluminum values are consistently underestimated. One of the reference samples also show an underestimation for magnesium and manganese, while the other displays only a slight underdosage. While potassium tends to be underestimated and titanium overestimated in one of the samples. The second sample's value, however, for these two elements remain mostly within the certified range. For calcium and iron, the measured values fall within the certified range. However, chromium and nickel show a systematic bias of over or under quantification of values. Vanadium and strontium present mixed results, where one reference sample falls within the certified values, while the other shows a systematic overestimation. Zirconium and rubidium show quite satisfactory results with respect to the certified values, while barium, phosphorus, and copper, which are elements often influenced by taphonomic processes, display a slight systematic shift of over or under quantification of values. Now I go to the collimator effect, to the impact of the collimator effect on the results, to be able to take into consideration the impact of using a 3 millimeter spot on the analysis of samples. We could see from the results that most elements don't have changed values, whether the 8 millimeter or 3 millimeter spot is used for the analysis. However, some elements show higher quantification with the 8 millimeter spot, while others show lower value. These variations, especially for these samples, do not necessarily indicate better or worse results or accuracy obtained by one spot more than the other. Now, even though we could verify the precision of the device, because through the years we have almost the same result, there's the same values of for the elements, we still face so we have verified the precision and repeatability of the device, we still face the challenge of the accuracy of the results. For that reason, several comparisons with other laboratory techniques, mainly such as wavelength dispersive X-ray fluorescence, have been carried out to obtain the slope and intercept in order to evaluate the accuracy and systematic bias of the equipment, and also to obtain the R-squared values for the data precision for ceramic analysis. The first comparisons took place in 2015, thanks to the collaboration with RR Laboratory in Lyon, which provided both the WD X-ray fluorescence results and the samples originally analyzed by Maurice Picon. The samples were analyzed using the portable X-ray fluorescence, and considering the WD results data as reference values, both methods have been compared. Later in 2021, an international network of portable X-ray fluorescence users has been established, whose main focus was the question of intercomparability of data. The results of the first comparisons showed that some elements had acceptable precision and accuracy. However, other elements showed less acceptable results, particularly in terms of accuracy, where the slope values deviated significantly from one. And finally, some elements showed values that were neither compatible nor acceptable regarding the portable equipment data. In general, this step highlighted the need for further work with more refined methodological approaches and additional comparisons to obtain more reliable results. For this reason, an international research network, Portable X-ray Fluorescence Ceramic Users Network Program, has been established since 2021 until 2025, led by the CNRS and financed by the French National Research Center, the Cnrs. For this network, various partners are working together to compare and share the data obtained by their portable equipment on ceramic materials. It consists of 13 laboratories from 8 different countries, where in France we have the CERALEX in Alexandria, the CCG and CEREG in Aix-en-Provence, and Archeosciences in Bordeaux. From the United Kingdom, we had the Fitch Laboratory in Athens, and from Greece, the Demokritos and the Demokritos in Athens and the University of Patras. From Cyprus, we had STAR-C and the Archaeological Research Institute of the University of Cyprus, VS from Austria, and the University of Cologne from Germany. And from Spain, we had the Archaeological and Archaeometric Research Unit of the University of Barcelona, and finally the Cnrs of Lebanon. The aim of this network project was not only to perform inter-comparisons between portable equipment, but also to eventually offer an inter-calibration for ceramic analysis. Ceramic materials can be used to answer a range of different questions, for which it is often necessary to use a series of complementary analysis to gain access to its microstructure. We have a range of tools at our disposal for studying archaeological ceramics to access its elemental compositions, such as the X-ray fluorescence. However, it should also always be considered that they are often inseparable from other mineralogical and molecular and microstructural data that are just as important in answering questions regarding the production or circulation of archaeological objects. Our knowledge of ceramics allow us to understand that this material is heterogeneous, unlike obsidian. If we look at the cross-section of the material, we will quickly understand the importance of the clay matrix, the grain effect, and their impacts and interactions with incoming and outgoing X-rays, entering and leaving the analysis surface. It can be said that the specific characteristics of ceramic material make them unsuitable for X-ray analysis without prior preparation. And this was one of the challenges that was faced by the pXRF Ceramic Users Network. And it is also for this reason that a common methodology was discussed, including the creation of a common kit. To this end, an initial selection of 18 examples of ceramics, archaeological ceramics, and international standards, has been made to create an intercalibration kit. Initially, 10 kits has been prepared in glass beads, were prepared by the CEREG by fusing powders and flux and distributed to the partners of the network. The same kit in powder forms was also provided to question the preparation of the analysis medium and to broaden the methodological questioning. Finally, some measurements also for this kit have been conducted directly on the sherds. In parallel, measurements were conducted by ICP-MS, by the CEREG, and the WD X-ray fluorescence, by the Fitch Laboratory and the Archaeological and Archaeometrics Research Unit of the University of Barcelona. The results of these two methods, the ICP-MS and the WD X-ray fluorescence, were almost identical and served as reference for the comparisons. The comparisons between ICP and WD and the pXRF yielded satisfactory results for major and minor elements, where despite the differences in the protocol of measurements between the different laboratories, the pXRF behaves similarly regarding the proximity and shift with respect to the reference data. Even though the beads have been chosen to facilitate the analysis of a homogeneous medium, thereby avoiding the heterogeneity of the clay matrix of the ceramic material, particularly those related to the inclusions, still a significant variability was observed between the equipment, most probably related to the dilution of the sample inside within the glass bead. Moreover, the measurements of the powders were more reliable, showing better detection and measurement accuracy. However, the shards that have been analyzed showed closer results to the reference measurements, but this is needed to be confirmed by increasing the number of samples and replicating the measurements by other teams. And so, accordingly, a new ceramic kit consisting of 18 fired bricks have been prepared from clays from known origins, with parallel analysis of WD and ICP conducted on them and used as reference values. During the meeting of the network in Cyprus in 2023, all the partners from the network met along with their portable equipment to analyze the same prepared set of ceramic kit. The results of this program and this meeting have been presented during the conference on methodological innovation in pXRF studies held in Vienna in 2024. And the article is to be published soon in the Études Alexandrines series of the CRLX in the beginning of 2026. The comparison between the results of the two equipment on this kit established by the network has helped with the calculation of correction factors that might be applied as a first step in the intercalibration of portable equipment, of portable data, to be closer to WD values for the problematic of data accuracy. This ceramic disc kit was not only used for the assessment of the portable equipment accuracy and precision, but also for the device factory calibration and stability. The kit has been measured twice using this Newton analyzer, once before the factory calibration that has been done in 2024, and once after. The comparisons between the results of this kit before and after factory calibration showed that most elements have similar results to the reference values, and that their concentrations remained almost the same before and after factory calibration, with similar equipment bias of systematic over or underestimation of certain elements, with very slight modifications sometimes in either precision or accuracy of data after equipment calibration. However, some elements showed better results after equipment calibration, especially phosphorus, an element which, however, is more related to the phonomic effect and is often of very limited use to us for pottery analysis. So to conclude, it is essential to pay attention to equipment performance for the acquirement of reliable data. The results presented here also shows the importance of regular follow-up and factory calibration to ensure the consistency of the results over time. Before using portable equipment, researchers must understand its behavior and limitation. Also, the date and year of each analysis should always be taken into consideration when using data for multivariate analysis, because the changes in protocol or equipment performance can affect the results. And of course, cross-correlation with reference laboratory methods such as WD X-ray fluorescence and ICP-MS is always critical to validate the data accuracy. Now, the next step we're going through for the network, which ended, is to discuss how to proceed with the data processing to intercompare data coming from different analyzers with a common method. Which common method should be applied here? Should we use calibration curves like the slope and intercept to correct our data? Or should we just publish the raw data and propose a common method to intercalibrate the results? And should these data be quantitative? Or should we go further and use other physical characteristics of the instrument itself, like the spectral calibration of element by element, which is what we're trying to do now with Michaela and Lee and Nadia. Thank you. And I'm sorry that I couldn't go through the 30 minutes completely. I tried, but it was not working.
No problem. Don't worry.
Thank you so much.
Thank you. Thank you very much, May. Thank you very much. It was very illuminating and very helpful, I think, to the community that of colleagues that are watching us. I'm sure it's very helpful, your experiences, and it gives some food for thought, you know, to further this problem of calibration. Now,
Yeah.
the next speaker, and then at the end we have discussions and questions, is Dr. Camille Frugier. I would with the topic Insights from MATEGEE program comparing pXRF data to characterize amphorae productions from Kition, Alexandria and Delos, the three sites. Camille is Doctor of Art History and Archaeology. Research themes. Her research interests range from trade and commerce routes in Gaul and around the Mediterranean basin in antiquity, production and distribution of ancient ceramics, particularly amphorae, through mineralogical and physicochemical characterization of materials like spectroscopy, petrography, elemental analysis, the manufacturing recipes and operational sequence established by ancient potters. Also, she is interested in ancient dietary practices through analysis of the contents of archaeological containers by gas chromatography, coupled with mass spec, and wine economy and viticulture development in the Picton region. In 2023, she obtained the PhD in Art History and Archaeology from the University of Poitiers on wine economy in Picton territory, first, third centuries AD, the study of the fusion and coding of regional amphorae, and in 2019 also obtained a master in archaeology, science in archaeology from archaeometry track of Bordeaux Montaigne University on fine earthwork and materials and mechanical properties. Dear Camille, the online podium is yours.
Thank you so much for this very nice introduction. Okay, I will. So, are you up? You should be able to see my screen now.
Perfect.
Perfect. Okay. So, good evening, everyone. Thank you so much to all the organizers, in particular Ioannis, you, Michaela, and Kaylee, who is not here, for giving me the opportunity to present some of my work and for everything that you did for this colloquium to take place. So I will be presenting you some insights from the MATEGEE program, which we work on together with Mai as well, on part of the work that we have been able to finish so far. So as I was saying, the study that I undertook is part of a big research project founded by the National Research Agency, the French National Research Agency. It's called Beyond the Stamps, Material and Production Strategies of Amphorae in the Hellenistic and Roman Periods. So it's led by the CE Alex and it's directed by Nadia Quentin. Its aim is to investigate amphorae production strategies in the Eastern Aegean between the 4th century BC and the 3rd century AD in collaboration with the British School at Athens and the University of Poitiers. The main goals are to examine the choice of raw materials and supplies and the evolution of manufacturing recipes, as well as observing repetitions and changes over time and space to try to provide interpretations in historical, sociological, and economic terms. And we aim to better understand the production strategies to further study trade and circulation of edible goods throughout the Mediterranean Sea. So this research relies on a large reference data set that was gathered over many years by the partner laboratories, especially by Mai herself. So she acquired more than 1,200 pXRF analysis for the CE Alex, and they're associated with approximately 600 think sections. And for the Fitch laboratory, it's around 350 WD XRF analysis associated with a collection reference of 250 thin sections of agent amphorae that are part of this research project. These amphorae, they mainly come from Greek cities that are known for amphorae productions, and they're colored in red on the map. Namely, it's the island of Rhodos, the city of Knidos, Kos, Samos, Chios, Lesbos, and Thasos. We also have comparative data from several consumption sites that include Kition, the main site which I'm going to be talking about tonight. But we also have consumption sites in Alexandria and in Kimentfares, in Delos, in Athens, and in Thasos. So the data set comprises actually most amphorae found in consumption context, even for the 7 islands that I previously cited. And it's mainly Hellenistic amphorae that were stamped, and those stamps were the ones that enable us to link them to the production Greek cities. So as I previously said, I will mainly be talking to you about some of the Kition samples that I previously studied as part of the first postdoctoral contract that I did for the MATEGEE program. So Kition is located in the southeast of the Cyprus island. It's beneath the modern Larnaca town. And it's located in a bay oriented towards the east and the Levant. It's an area that was rich in agricultural and mineral resources, which made it an important commercial stop in the Eastern Mediterranean. It was founded in the 13th century BC, and it experienced a continuous occupation during and it experienced a continuous occupation through the classical, from the 13th century BC, to the classical period. The city itself developed around 2 low plateaus. In the north, there was the Qatari area with the craft workshops, especially it was copper working, and a temple district that was attested from the first millennia BC onwards. And in the southeast, it was the Bambula area with temples and a harbor that you can see on the pictures that was set along a lagoon. And in the Bronze Age, this harbor was a natural anchorage. And in the classical period, it was then equipped with the stone ramps for warships. Some sediment core studies showed a classical pattern of the coastal evolution. Around the city's foundation in the 18th century BC, the area formed an open bay that was suitable for harbor activities. But then, between the 7th and the 5th century BC, a pebble barrier formed to the north of the Bambula sector, which transformed the Qatari Bay into a lagoon. And by the Roman period, the Kition Bambula area had become a silting marshland. In the Kition Bambula sector, excavations were carried out from 1995 to 1998 in the former harbor. And it yielded a large ceramic assemblage that was initially studied once the excavations ended, but then studied again in 2017 by Sandrine Marquier and Séverine Lemaitre. And this is their results that I'm going to be showing you in the next slides. And this is what permitted my study of the Kition samples. So the first thing that we should note is that amphorae form an exceptional proportion of the ceramic assemblage because it represents nearly 50% of the minimum number of individuals, which is huge and which normally doesn't happen. The full inventory, including material found outside the harbor zone, amounts to around 1,492 short fragments, which corresponds to a minimum number of individuals of 622. Most of the assemblage belongs to the Roman period, with a few Hellenistic and classical shards. And the amphorae assemblage is generally well preserved, and it originates from all over the Mediterranean basin. Okay, so the detailed inventory that was made both taking typology and macroscopic observation of the fabrics shows that around 80% of the fragments and 88% of the minimum number of individuals come from the Eastern Mediterranean. The Western Mediterranean imports are quite rare because they're around 10% of the fragments and only 7% of the minimum number of individuals. And finally, 15% of the fragments are of unknown origin. Within the ceramics coming from the Eastern Mediterranean group, Aegean amphorae are particularly numerous. So they amount to 412 fragments, which is roughly 209 individuals. So it's approximately 28% of the assemblage of the whole amphorae assemblage. And it's more than 1/3 of the minimum number of individuals. So they are the most common imports, like the main imports, and they're followed closely by the Levantine amphorae that are a little less numerous. Donc, as I said, this inventory was based on fabric observation and on typological study, which allowed Séverine and Sandrine to propose initial origins for the Aegean material, which is what you're seeing right now. And these include productions from Rhodos, Knidos, Kos, and its region, which are of particular interest for us inside MATEGEE, but also a number of vessels that are likely originating from the southwest and the west coast of Anatolia. In contrast, amphorae from Samos, Chios, Lesbos, and Thasos are only weakly represented, and a third group of samples seems to be related to Cretan, Ephesian, or Melian productions, which fall outside of the MATEGEE program. And we notice also that some of the samples remain unattributed for now. So, given the goals of the MATEGEE project and the availability of material at Kition and in the reference collections, we defined several research priorities for the Kition material, and it was decided that we would primarily focus on Rhodian, Cnidian, Coan, and Western Anatolian productions. And first, I'm going to present very, very briefly some of the Knidos amphorae, just to show you, because it's one of the main, working on those amphoraes was one of the main goals of the MATEGEE program. So here you can see almost all of the samples that were available for Kition that are supposedly coming from Knidos. They all belong to the same type, which is called Mao 38, and most of them are from the Roman period. Just so you know, black dots correspond to photographed amphorae, and orange dots to the ones that we could sample. the Dressel 2-4 and Dressel 5 amphorae assemblage was also of particular interest because as though it was originated from Kos, the Dressel 2-4 type was also produced in other Greek cities, including Rhodos, Knidos, Ephesus, and Chios. And we also know that several of the production centers, were located alongside the southwestern Anatolian coast. So one of the objectives of the project was to identify, where possible, the specific workshops that produced those Dressel 2-4 amphorae found in Kition. You can see some of the drawings that were made here of those amphorae. But here today, we're going to focus particularly on Rhodian samples, which arose many questions. The first concern was, could we determine their precise origin? Is it Rhodos, the Rhodos island itself, or the Rhodian Piraeus? Because a number of workshops are attested on the Anatolian coast that was part of the Rhodos city. We would also want to assess whether Rhodian workshops, Rhodian workshops were still exporting amphorae during the imperial period, because most of the Kition set dates from the imperial period. And then we would have liked also to focus on some unidentified production, which I will be discussing a little later. So, as I was saying, the territory of Rhodos extended beyond the island itself and included enclaves alongside the opposite Anatolian shore. And this area was known as the Rhodian Piraeus, and it contained several pottery workshops. And you can see some of them on the map. And it's important because all of the Rhodian amphorae, whether they were produced on the island itself or on the Rhodian Piraeus, received a Rhodian stamp. So when in the collection references, when we see a Rhodian stamp, we cannot say if the amphorae is coming from the continent or from the Rhodos island itself. We have for Rhodos a few Hellenistic samples, but yet again, most of the data set is Roman amphorae. I will just show you very quickly the unidentified production, which we will not be discussing too much tonight, but they are still interesting. So for now, they're called PNI 30 to 32, so unidentified production. Unidentified production, but it's in French. So the three types are here, and as of today, we do not have any idea of where they could be originated, though it was suggested when the macroscopic study was undertaken that they could be Rhodian amphorae. So we would like to assess that as well as part of the project. Within the MATEGEE framework, our objective was to refine the previous provenance proposals that were made by Sandrine and Séverine through a systematic macroscopic examination, elemental analysis of all the samples, and petrographical study of parts of the assemblage, not all the assemblage. And the elemental analysis were performed using a Niton XL3T Gold Plus, which was loaned by the CE Alex. And that allowed us to measure 20 elements according to the protocol that Mai previously presented to you. So we used, for analyzing the Kition samples, the same model that Mai used to analyze, the Alexandrian collections, but it was not the same device itself. Most of the Alexandrian collections were analyzed with what we will call the Niton 1, which is this one, the number 65941, and the Kition samples were analyzed using the Niton 2, which is the second one here. So as part of the iron ceramic users network that Mai also previously talked about, the ceramic kit that was created as part of the network was analyzed by both the devices, and it enabled Mai to determine correction factors to diminish the shift that is observed between the two, those two analyses. Okay, and corrections were applied in two different manners. The first one was with respect to WDXRF data, and the second one was from one knitter with respect to the other. So this shows for the ceramic kit the results before and after applying the correction factors with respect to the WDXRF data. So both data sets acquired with the two Nitons were corrected with regard to this WDXRF data. Or might also determine correcting factors with respect to Niton 2 towards Niton 1, because the Niton 1 was the one that was the most used, so it made sense to choose this one as a reference. And here for Kition, this is the type of correction that we used on our data. As I said, we are mostly going to talk about Rhodos as a case study, but only the samples positively attributed to Rhodos when the macroscopic study was undertaken were included in the diagrams and the data treatment that I will show you. So all the unidentified production that I was just telling you about were discarded, because we could already see both from petrographic and chemical data analysis that they had mineralogical and chemical, different mineralogical and chemical composition. So the unidentified production, the PNI 30 to 32 are here in yellow, and the samples, all the samples that were positively attributed to Rhodos just on the base of the macroscopic study are here in orange, and this is the samples that we're going to be talking about. And as you can see, they're already quite heterogeneous themselves. So here you can see macroscopic images and PPL pictures for almost all the Rhodian samples coming from Kition, well, all the supposedly Rhodian samples coming from Kition. So now I'm going to present you the factor corrections. So we noticed that the shifts in the measurement vary depending on analyzed elements. So they range from 0.5% for silica oxide up to 36% for rubidium, an element that we do not detect well. For silica, iron, chromium, and zinc, shifts are low, less than 5%, or around a little bit more than 6% for iron. But on the other end, for aluminum, potassium, titanium oxides, strontium, rubidium, and zirconium, we observed underestimation that range from 17 to 22% for major elements, and from 25 to 36% for the trace elements. And finally, for calcium, magnesium, manganese oxides, and for nickel, vanadium, and niobium, we had overestimations with the second Knighton that we used, and the shifts ranged from 10 to 20%, yes, for the oxides, and they ranged from 6 to 18% for trace elements. So here you can see Kition data before and after applying the correcting factors with respect to all the analyzed samples for Rhodas by Mai. So the collection for Rhodas from the CE Alex, analyzed mostly with Knighton 1, and the Kition samples are in red, and as you can see, it's very useful and important to apply those correcting factors, because after that, after the correction, you can see that some of the Kition samples lay within one of the chemical groups for Rhodas that Mai determined. So it's chemical group D. But what came as a surprise is that those samples that seem to work to fall within the chemical group D for Rhodas that Mai determined are actually samples that were not I would not for sure attribute to Rhodas if I take the petrographic side of the study. When I looked at the thin sections of Kition and the thick sections of the collection references, I could see a lot of similarity, but I couldn't be sure that these samples were indeed Rhodian. On the other hand, all the group here that is a little above the chemical group T was showing more similarities with the thin sections of Rhodas that the CE Alex and the Fitch laboratory possess. For now, we have two explanations two ideas for explaining this. The first one is the difference in chronology that we know exists between the reference collections, which are mostly Hellenistic, and the Kition samples, which are mostly from the Roman periods. And the second idea is that actually this chemical group D is not really well known in thin sections, because there's only one sample in the CE Alex and new ones are coming soon. So maybe when those new thin sections arrive, we will be able to understand more why the Kition samples that didn't share all the Rhodian characteristics are falling within this group. So yeah, we still have a lot of work to do, and I thank you for your attention. Oh, sorry, I forgot to change the slide. I actually had a slide for everything that I just explained. Yeah, thank you for your attention.
Thank you very much, Camille. Both actually presentations are so related that I suppose there could be several questions. So, Michaela, can you ask the first about the first speaker if there is any questions?
Yes, absolutely.
Or for both, yeah.
Yes. Are there any questions? Don't be shy. There's always nobody daring to speak up. But surprise, I would have some. So if nobody else wants to, then I would just go ahead. The first ones are for Mai, and they are in relation to the precision testing. So I just wanted to know, you said that you defined how much of error is okay for precision when you define the proper measurement time. And I might have missed that, but what is the percentage of error, or how did you define the error that is acceptable?
It was the error that was obtained by the device itself. So when you do the analysis, actually from the Newton itself, it gives you the composition. When you acquire the data, it gives you the composition and the error for each element. And this error was used to calculate the percentage of error for each element that was gained or lost when changing the time per each filter.
All right, so you took just the measurement value and the standard deviation?
No, from the raw data of the device. It gives you error values for each element, depending on the limit of detection and on the composition itself. It gives you a certain error from the data from the device itself. And this error was used to calculate the percentage of error per each element. Because the tests were done by changing the filter time from 30 to 60 to 90 to 120 for each filter. And these errors, these different errors with respect to the different times was calculated. It was obtained from the device, and then the percentage was calculated with respect to the composition. How much was lost or gained.
All right. All right. And you also mentioned that you do a precision test at least half a year, every half year. How does that work in a practical way? How do you do that?
You just measure the same point for 50 consecutive times, and then you calculate the average, the standard deviation, and the precision from the standard deviation and the average.
And what's your benchmark there? How much is acceptable?
The acceptable usually is until 5% of precision. 10% depending on the element, if it's essential or not, but 10% is a little bit high. And then above 10%, I just send the device to be factory calibrated.
All right. Is that for, if it happens to one element that it is too high, do you already send it in? Or?
I mean, phosphorus and magnesium are the easiest to fall.
Yeah.
So it depends on the element. If the magnesium stays at 10, I just don't send the device. And then if I have more than one element that just keeps changing and keeps having lower precision, I just send the device to be calibrated anyways. But the first elements to fall, that's for sure, it's magnesium and phosphorus.
Thank you.
Welcome.
Are there other questions? Detlef, you unmuted yourself. Did you wanted to say something?
No, I was kicked out. I had a technical problem, obviously.
Oh, no.
Now I'm back. I'm back.
I'm sorry. All right, if there's nobody else daring, then I have another one. I'm sorry. You showed things I'm interested in, so I have to ask. And it's about the correction, again, that you did for Camille's data. So I don't know if it's Mai or Camille who's better equipped to answer, so kind of to both of you. I wasn't sure. You said that, Camille, if I understood that right, that the data was corrected in regard to the VDXRF data and then in regard to each other.
Yeah, we were making like trial and errors to try which correction might be applied, because you remember in October when I did my presentation, it was just correcting the pXRF values to WD data to just see if the shift is gone or not. And that worked. So for this, we are just comparing portable analyzers data, and I didn't know if it's best to calculate correction factors for one equipment with respect to the WD data and then correct the second equipment to the WD data and compare both of them, or just correct the values of the second equipment to be able to be closer to the values from the first equipment. And we're still testing, actually. It was just to see how it works, but we're still testing that to see which mean is better to correct the values. But this also only concerns when we're comparing more than data coming from different equipment. If we're using only one equipment, we don't need correction.
Yeah. Did you try it with Camille's data? What happens if you do the different ways of correcting? Do you always end up with the same clusters?
For example, we only performed with Camille a principal component analysis, and for both we actually arrive at the same results. But with the correction, when you correct using with respect both values with respect to the WD data, we arrive actually at more factors.
Yeah.
But the results are more or less the same.
All right. Thank you.
But it's still under testing. We just tried this recently with Camille, so we didn't really go a lot into the details and the protocol. So we're still trying to see which is the best way to be able to use the network work, all that we have been doing since 5 years now, to correct our values. And maybe the cloud cal, I'm still bugging Lee all the time with questions to be able to understand how to apply that, and maybe that would work better. So we're still seeing.
There is a question by Kidan.
Yes, thank you, Mai. Yeah, and the Camille for the presentations. My question is to Mai. Regarding the disks you have analyzed, are they homogenized? Because heterogeneity is one of the great problems in ceramic investigation.
Homogenized. We sent actually the clay samples to Patras, which homogenized the clay, and they prepared the disks. For the publication, all the teams analyzed the same disks just to avoid any kind of shift between the different kits. But actually, we just received the thin sections for the disks, and we can see also that it's not really as homogeneous as we have wished it to be. But at least the kits, we have the reference values from the WD and the ICP. And usually, the protocol set was supposed to be homogenized by Patras University.
And the great deviations you have observed with regards to phosphorus and magnesium, is that observed for the other lighter elements? And if it's not, what do you think is the cause? Because when you analyze it by different instruments, there is great deviation in them.
Magnesium, not really. It depends on the instrument. Actually, each element, each element, how it acts with respect to accuracy, and if you're speaking about the different equipment, each equipment behaves differently. So sometimes for a certain element, like magnesium, for example, for a certain equipment, it's really well detected, and for others, the deviation is really high. So either correction is added or the element is eliminated. So it all depends on the choices that you make when you're doing the study. For me, here I cannot, the portable equipment is very essential because I don't have WD or ICP or other laboratory technique. It's not a complementary as much as it's the main method I use for the chemical compositions. But phosphorus, magnesium, for example, I can say that copper was not well detected. Zinc, yttrium was not detected by all the equipment. Some equipments don't detect it at all. And this is related mostly, I think, to the factor calibration. And phosphorus, I will not say magnesium because magnesium is not well detected. It all depends on also the limits of detection and how much of this element is present in the material. So it's phosphorus, copper, zinc, yttrium, and depending on the equipment, I can say vanadium and potassium. We have a problem with potassium, actually.
Thank you.
You're welcome.
Are there any more questions? I don't have more.
Oh, really? That's
have
very
one.
surprising.
Hello.
Howdy. So quick question, Mai. When you
Oh.
comment on copper, vanadium, and these other elements not being detectable, in your estimation, is that a factory calibration issue
No,
or an equipment hardware issue that they're just not picking them up?
no, I'm not saying that they are not detectable. They are not really well detected. If we compare the pXRF data with the WD data, the results are not really good or comparable. It's the yttrium I'm talking about, because I know that I have two nitrogens, one of them that detects yttrium and the other no. And I think that's a factory calibration problem. And I think that you have to go there to say that I need this device to detect yttrium.
Yeah.
So that's only with yttrium, but for the other elements, I think it's related more for, I don't know if it's a factory calibration problem or if it's a limit of detection problem. I think we're going to discuss that in a few days.
May I ask a question?
Yeah, sure. Go ahead.
Did you ever check the spectra, the original spectra? Check for peak sizes? You will recognize that your magnesium, aluminum, and silicon peaks, as well as vanadium and chromium, will most likely be very, very small. It is almost impossible with pXRF to reliably determine vanadium and chromium concentrations in typical clays, because the region, the lower Z region, is overcrowded, and the software typically cannot distinguish between very small peaks. Lee knows that from his former work with Puka.
Yeah, we are working with Lee on the spectral data, but if I understood correctly, you're saying that it's impossible for pXRF to detect chromium and vanadium?
Yeah, because the peaks are too small. There may be some clays with higher chromium values, but typically the chromium value particularly, and vanadium as well, there is peak overlay from other elements which has to be deducted, and the peaks are in general too small.
Yeah, Detlef is correct, because it's typically speaking, the big problem element there is barium's L lines overlap with titanium, which we all know, vanadium. There's actually a little L gamma right below chromium as well, which makes it very challenging. For vanadium, you can sometimes be able, if there's enough of it there, a titanium and barium correction simultaneously works pretty well, but you need a lot of standards, and most, something 40 plus to be able to get it reliably.
I'm just checking because I do not, I mean, how can then we explain, we're only talking about portable data here. We're not talking about WD or other methods.
Yes, portable.
So how can, for example, we get comparable data between, how can we get the same, now I'm talking about the quantitative, not qualitative, but how can we get good chromium detection or data that is close to the same values obtained by a WD or an ICP?
Oh, I mean, I don't think it'll be equivalent to ICP or WD, but if you want to try it with pXRF and you've got high enough concentrations of chromium, you'd want a vanadium correction because chromium K alpha is sitting on vanadium K beta, and you'd also probably want a barium correction as well. And with those two corrections, it's sort of, if you have too few standards, you'll have covariance, which will cause an artificially good R-squared value. You can cross-validate to check. But like, that might work, but I think what Detlef's comment pertains to is that in most normal ceramic materials, the actual amount of vanadium chromium is going to be so little that even with these corrections, it's going to be more noise than signal. That said, I have seen some crazy vanadium on some Cyprus ceramic sherds in the past, and it's usually inclusions, but it's possible to sometimes get strong signal, but depends on the mineralogy.
Okay. Okay, and in this case, do you think the correction might work or not for these elements?
I mean, costs nothing to try. I wouldn't rule that out until you try, but if it doesn't work with those two corrections, probably doomed.
Yeah.
The general experience with different brands and with different methods. Also, if you will compare pXRF with powder EDXRF, at very low concentration, these methods fail. And this is typically below 20 ppm or below 10 ppm. Nevertheless, many factory calibrations still produce values at these low concentrations, and you cannot trust these values which the factory calibration provides you. And the only way to escape is to inspect the spectra, whether the element is present or not.
Okay. Okay.
Yeah.
Yeah.
Thank you so much.
Here we started to do that, right, Mai? We started with factory calibration spreadsheet data and worked from that. And then now in the last 1 to 2 years, we started to work with the spectra as well to figure out, especially stuff like that.
Yeah.
What's there, what's not there, how can we, what's the best way?
Yeah.
And there we might also mention the work that Michelle and the Australasian network is doing, who also did some device intercomparisons and will also be published in the conference proceedings, who worked with the spectra data. So there are two teams kind of trying to figure out what do we do? How do we deal with those spreadsheets? How do we get the best approach to compare data? And yeah, just to plug that, because we're talking conferences, there is a conference on pXRF coming up on the 30th of March next year in Vienna, and the call for papers is still open until end of the month. So
the end of the month is in 4 days.
It is, but it's still in 4 days.
We will talk about that.
For sure.
Yeah.
Ellery is putting something in the chat, so I guess he can't talk right now. So he says, geologists using EMPA VD have been dealing with titanium, vanadium, chromium overlaps for decades, so there are some approaches there to consult. So thank you for the comment. So again, having to go out of the ecology, ecometric bubble to not repeat stuff that's already done. Does anybody else have a comment or another question? Anything on the ecological side about the amphorae? Janis, do you want to know something? He's fine. And we lost Anno, so he would be the guy to ask more about the amphorae. So, all right, if there is no more questions, then we have been quick today. We have our next colloquium on the 17th of December, if I'm not mistaken, and it's going to be Ellery and Kyle Freud who will be talking about more pXRF exciting stuff like standards and the effect of firing on our material. And yeah, is there anything you want to say Ioannis's closing remarks?
No, I'm very pleased today. You know, it was a very fruitful and useful discussion and content of the two presentations, and it shows up, you know, once more, you know, the importance of having this global portable XRF core group, you know, that try to unite forces and make a final somehow calibration method for using pXRF by every archaeologist in the field and in the laboratory as well, in the museum.
Thank you. Thank you to both of the speakers. Thank you for your amazing presentations. Thank you for all who came by and listened, and hope to see you all at the next colloquium.